causal diamond. Bousso first encountered the measure problem in the 1990s as a graduate student. Working with Stephen Hawking, the doyen of black hole physics, black holes prove there is no such thing as an omniscient measurer, because someone inside the black hole's event horizon, beyond which no light can escape, has access to different information and events from someone outside, and vice versa. Bousso and other black hole specialists came to think such a rule must be more general, he said. Precluding solutions to the measure problem along the lines of the immortal watcher, physics is universal, so we've got to formulate what an observer can, in principle, measure. This insight led Bousso to develop a multiverse measure that removes infinity from the equation altogether. Instead of looking at all of space-time, he homes in on a finite patch of the multiverse called a causal diamond, representing the largest swath accessible to a single observer traveling from the beginning of time to the end of time. The finite boundaries of a causal diamond are formed by the intersection of two cones of light, like the dispersing rays from a pair of flashlights pointed toward each other in the dark. One cone points outward from the moment matter was created after a Big Bang, the earliest conceivable birth of an observer, and the other aims backward from the farthest reach of our future horizon, the moment when the causal diamond becomes an empty, timeless void and the observer can no longer access information linking cause to effect. Alina Shmahello / Quanta Magazine, source. Raphael Bousso, Ronnie Harnick, Graham Cripps and Gilad Perez. The infinite multiverse can be divided into finite regions called causal diamonds that range from large and rare with many observers, left, to small and common, with few observers, right. In this scenario, causal diamonds like ours should be large enough to give rise to many observers but small enough to be relatively common. Bousso is not interested in what goes on outside the causal diamond, where infinitely variable, endlessly recursive events are unknowable, in the same way that information about what goes on outside a black hole cannot be accessed by the poor soul trapped inside. If one accepts that the finite diamond, being all anyone can ever measure, is also all there is, Bousso said, then there is indeed no longer a measure problem. In 2006, Bousso realized that his causal diamond measure lent itself to an even-handed way of predicting the expected value of the cosmological constant. Causal diamonds with smaller values of would produce more entropy, a quantity related to disorder or degradation of energy, and Bousso postulated that entropy could serve as a proxy for complexity, and thus for the presence of observers. Unlike other ways of counting observers, entropy can be calculated using trusted thermodynamic equations. With this approach, Bousso said, comparing universes is no more exotic than comparing pools of water to roomfuls of air. Using astrophysical data, Bousso and his collaborators Ronnie Harnick, Graham Cripps and Gilad Perez calculated the overall rate of entropy production in our universe, which primarily comes from light scattering off cosmic dust. The calculation predicted a statistical range of expected values of the known value, 10,123, rests just left of the median. We honestly didn't see it coming, Bousso said. It's really nice, because the prediction is very robust. Making predictions. Bousso and his collaborators' causal diamond measure has now racked up a number of successes. It offers a solution to a mystery of cosmology called the why now problem, which asks why we happen to live at a time when the effects of matter and vacuum energy are comparable, so that the expansion of the universe recently switched from slowing down, signifying a matter-dominated epoch, to speeding up, a vacuum energy-dominated epoch. Bousso's theory suggests it is only natural that we find ourselves at this juncture. The most entropy is produced, and therefore the most observers exist, when universes contain equal parts vacuum energy and matter. In 2010, Harnick and Bousso used their idea to explain the flatness of the universe and the amount of infrared radiation emitted by cosmic dust. Last year, Bousso and his Berkeley colleague Lawrence Hall reported that observers made of protons and neutrons, like us, will live in universes where the amount of ordinary matter and dark matter are comparable, as is the case here. Right now the causal patch looks really good, Bousso said. A lot of things work out unexpectedly well, and I do not know of other measures that come anywhere close to reproducing these successes, or featuring comparable successes. The causal diamond measure falls short in a few ways, however. It does not gauge the probabilities of universes with negative values of the cosmological constant, and its predictions depend sensitively on assumptions about the early universe, at the inception of the future-pointing light cone, but researchers in the field recognize its promise. By sidestepping the infinities underlying the measure problem, the causal diamond is an oasis of finitude into which we can sink our teeth, said Andreas Albrecht, a theoretical physicist at the University of California, Davis, and one of the early architects of inflation. Kilban, who like Bousseau began his career as a black hole specialist, said the idea of a causal patch such as an entropy-producing diamond is bound to be an ingredient of the final solution to the measure problem. He, Guth, Vilenkin and many other physicists consider it a powerful and compelling approach, but they continue to work on their own measures of the multiverse. Few consider the problem to be solved. Every measure involves many assumptions, beyond merely that the multiverse exists. For example, predictions of the expected range of constants like and the Higgs mass always speculate that bubbles tend to have larger constants. Clearly, this is a work in progress. The multiverse is regarded either as an open question or off the wall, Guth said, but ultimately, if the multiverse does become a standard part of science, it will be on the basis that it's the most plausible explanation of the fine-tunings that we see in nature. Perhaps these multiverse theorists have chosen a Sisyphean task, perhaps they will never settle the two-headed co-question. Some researchers are taking a different route to testing the multiverse. Rather than rifle through the infinite possibilities of the equations, they are scanning the finite sky for the ultimate Hail Mary pass, the faint tremor from an ancient bubble collision.